The Parker Solar Probe's daring mission to touch the Sun represents a pinnacle of human ingenuity and a relentless pursuit of scientific understanding. More than just a flyby, this mission plunges a spacecraft into the Sun's corona, the outermost layer of its atmosphere, an environment of extreme heat and radiation. This audacious endeavor required pushing the boundaries of materials science, thermal engineering, orbital mechanics, and communication technology. The story of the Parker Solar Probe is a testament to meticulous planning, innovative engineering, and a deep-seated desire to unravel the mysteries of our star. The primary scientific objectives of the Parker Solar Probe are threefold: to trace the flow of energy that heats the corona and accelerates the solar wind, to determine the structure and dynamics of the plasma and magnetic fields at the sources of the solar wind, and to explore the mechanisms that accelerate and transport energetic particles. These objectives translate into a mission profile that involves repeatedly flying through the corona, getting closer to the Sun than any spacecraft before. The most formidable challenge in designing the Parker Solar Probe was protecting it from the Sun's intense heat and radiation. At its closest approach, the probe faces temperatures reaching nearly 2,500 degrees Fahrenheit, 1,370 degrees Celsius, and intense solar radiation. The key to surviving this extreme environment lies in the spacecraft's thermal protection system (TPS), the heat shield. The TPS is a marvel of materials science. It consists of a 4.5-inch thick carbon-carbon composite shield. Carbon-carbon is a material known for its exceptional strength and ability to withstand incredibly high temperatures. It is created by reinforcing carbon fiber with a carbon matrix, resulting in a material that is both lightweight and extremely durable. This composite is further enhanced by a layer of lightweight carbon foam sandwiched between two carbon-carbon panels. This foam provides additional insulation, further reducing the amount of heat that reaches the spacecraft's instruments. The sun-facing side of the TPS is coated with a specially formulated white ceramic paint. This paint is designed to reflect as much sunlight as possible, minimizing the amount of heat absorbed by the shield. The combination of the carbon-carbon composite, the carbon foam, and the white coating allows the TPS to effectively block the vast majority of the sun's heat, keeping the spacecraft's instruments at a relatively comfortable temperature of around 85 degrees Fahrenheit, 29 degrees Celsius. Beyond the heat shield, the spacecraft itself is constructed from materials chosen for their ability to withstand extreme temperatures and radiation. The primary structure is made of lightweight aluminum alloy, but components closer to the Sun utilize more heat-resistant materials like titanium and niobium alloys. These materials are chosen for their high melting points and their resistance to degradation from solar radiation. Managing the spacecraft's temperature is a complex undertaking that goes beyond the heat shield. A sophisticated thermal management system is employed to dissipate heat away from the spacecraft and maintain optimal temperatures for the sensitive scientific instruments. This system includes radiators, which radiate excess heat into space, and intricate cooling systems that circulate fluids to transfer heat away from critical components. The Parker Solar Probe's trajectory is a carefully orchestrated dance with Venus. The probe uses gravity assists from Venus to gradually reduce its orbital period and bring it closer to the Sun. These gravity assists are calculated using the principles of celestial mechanics, specifically Newton's law of universal gravitation. F equals G asterisk m1 asterisk square meter, RA, where F is the gravitational force, G, the gravitational constant, m1 and square meter are the masses of the two objects Venus and the probe, and r is the distance between their centers. By precisely timing its flybys of Venus, the probe can use the planet's gravity to alter its trajectory and reduce its velocity relative to the Sun. This allows it to gradually lower its perihelion, the point of closest approach, to the Sun over a series of orbits. The probe's orbital period, the time it takes to complete one orbit around the Sun, is calculated using Kepler's third law. PA equals 40 to per gram m asterisk. AA, where P is the orbital period. G is the gravitational constant, m is the mass of the Sun, and A is the semi-major axis of the orbit. The probe's velocity at different points in its orbit can be calculated using the Weiss-Viva equation. VA equals gm asterisk 2, R1. A, where V is the velocity. G is the gravitational constant, m is the mass of the Sun, R is the distance from the Sun, and A is the semi-major axis of the orbit. As the Parker Solar Probe approaches the Sun, it faces intense solar radiation. The intensity of this radiation is calculated using the inverse square law, I equals L, for pi Ra, where I is the intensity, L is the Sun's luminosity, and R is the distance from the Sun. Determining the actual temperature of the heat shield is a complex process that involves intricate calculations considering factors such as solar radiation, heat absorption, and heat dissipation. These calculations often rely on sophisticated numerical methods and thermal modeling software. Communicating with the Parker Solar Probe when it is close to the Sun presents significant challenges. The Sun's intense electromagnetic activity can interfere with radio signals, making it difficult to maintain reliable communication. To overcome this, the probe is equipped with high-gain antennas and utilizes sophisticated communication protocols. These protocols are designed to maximize the signal strength and minimize the impact of solar interference. The Parker Solar Probe's mission is a testament to the power of human ingenuity and our unwavering pursuit of scientific knowledge. It represents a significant step forward in our understanding of the Sun and its influence on the solar system. By venturing closer to our star than ever before, the Parker Solar Probe is providing invaluable data that is helping us to unlock the secrets of the Sun's behavior and its impact on Earth. The mission is not just about exploring the Sun. It's about understanding the fundamental processes that drive our star and shape the space environment in which we live. The data collected by the Parker Solar Probe will continue to be analyzed for years to come, providing new insights into the Sun and its complex interactions with the solar system. This bold expedition into the Sun's domain is a shining example of human innovation and our enduring quest to explore the universe around us. It is a story of meticulous planning, innovative engineering, and the relentless pursuit of knowledge, a true testament to the spirit of scientific accomplishment.